Today I'm going to demonstrate how to define user programmable features in Ansys. For demonstration purpose, I'm going to take an example of defining user defined material model in Ansys release 19.0. In this demonstration, I'm going to explain how to write Fortran based subroutine for bilinear isotropic hardening plasticity constitutive model. This bilinear isotropic plasticity model is available as a standard material model in Ansys. So we can compare the results from user defined material model with standard Ansys material model for the correctness of implementation of user defined constitutive model in Ansys. To write any user defined features, one can use Fortran or C program. It is important to use a compatible version of Fortran compiler and Visual Studio to correctly compile the Fortran program and link with other subroutines of Ansys so that one can successfully complete the analysis. To understand the correct version of compiler requirement for particular version of Ansys, open Ansys help manual. I am using version 19 for this demonstration purpose. Okay, open Ansys 19 Ansys help manual. Go to installation and licensing. Installation licensing. I'm going to demonstrate this on Windows platform. So I'm going to Windows platform. Platform details, compiler requirements. Okay, we are going to write a user programmable subroutine for mechanical APDL or for workbench. So we need Visual Studio 2012 and Intel Fortran compiler 5.0.7. It is highly recommended to use the exact version of Fortran and Visual Studio as mentioned in the help manual. If the versions different than what is mentioned in the help manual is used, there is no guarantee that the compilation and linking will be correct. Having said this, this is the first requirement. One need to have these two programs apart from Ansys installed on the machine. Second thing is to enable user programmable feature. During installation, one need to make sure the customization files for user programmable feature is enabled during installation. If you are not enabled this section during installation, please go back to your setup.exe, reinstall. You can untick all other programs except this, so only this will additionally get installed this time. Once this feature is enabled during installation, once you go to Ansys installation directory, program files Ansys Inc version 19, inside Ansys folder you will see a folder called custom. This custom folder will appear only if this feature is activated during installation. Before we disturb any one of the standard installation, it is highly recommended to take a backup copy of this custom folder. so that if anything goes wrong, we can delete whatever the modification we have done on this custom folder and restore the original custom folder. Okay, get inside this custom folder, user win64. If you go inside this examples, there is a file called usermat.f. You could open this Fortran file with any text editor or Visual Studio as such. So I'm comfortable with using Notepad++, so I'm using Notepad++. So this file demonstrates the subroutine for bilinear isotropic hardening material model. Again, one more thing to keep in mind, that if you are trying to implement any user-defined material model, you should be completely familiar with the mathematics and the physics behind that particular material model. So you should know all the steps involved in writing a subroutine for material constitutive law implementation. Okay, this bilinear material model can be used for different types of elements. Say for example, it can be used for 1D bar elements or beam elements, shell elements, solid elements, and so on. This material model has, this usermat.f file contains the subroutine for 3D model, also for beams, also for 1Ds, and so on. So now let's pay attention to only the 3D material model. So if you look at this, this is basically a function what we are going to call 3D. It will have a lot of input arguments. So if you want to formulate a constitutive model, you have to get some of the parameters from the standard Ansys solver. Like when you start the iteration, what is the stress level that exists in every integration point, and what is the material ID, what is the element ID, and so on. So all the inputs available to this subroutine are listed here. It means that you can get any one of these variable from standard Ansys calculation. These are all input and output arguments. This is the output arguments. We have to pass it back to Ansys such that whatever the calculation is done in this subroutine is linked with rest of the subroutines that Ansys is shipping with standard installation. Okay, here is some of the standard terminologies. If it is a 3D model, there will be 6 components of stress, 3 normal stress and 3 shear stresses, and there is if you want to understand what is this income, go back to this input section somewhere. Say income means direct and end shear stress. In addition to this, there are some good resources available in open literature. If you go to Google search and search for Ansys user material subroutine, the second link what you get is a very good reference material. Okay, say if you go here and say for example, if you search for ncomp, some examples are given here, and if you can go back, say for example, ncomp is total number of stress and strain components at material point. Okay, so 3 direct stresses and 3 shear stresses, and so on. So you could get a brief description of these parameter in this usermat.f file itself, which comes along with the installation. If you need little more detailed information about these material, you can go to this link, and you can understand from this particular document. And also there is another good document that you get in this link. If you could open, This is from Ansys standard training material for user programmable feature course, and this also gives some good information about implementing user-defined material models in Ansys and what is the terminologies that we use. Different program may use different indexes for stress and strains and so on. Okay, so here is a good description as well. Okay, so coming to this, whatever the parameters that has to be declared in standard Fortran, we am defining some more additional parameter for my internal calculation purpose. There are quite a lot of local variables. Some are of vector type, some are of scalar type, some are of array type, and so on. All these things need to be defined here. Once this is done, then we are going to implement all the actual calculation. Say for this bilinear isotropic hardening material model, we need to supply Young's modulus, Poisson's ratio, yield stress, and the fourth input is the tangent modulus of the material. These are all the four inputs that we are going to get from Ansys input file. Say for example, if you look at the Ansys input file, say here is my material. See, TB user, it means that this is a user defined material model for material number 2, okay, and which has four this has four input parameters. Those four are nothing but Young's modulus, Poisson's ratio, yield stress, and tangent modulus. Okay, so this property 1 will get the Young's modulus value, property 2 will get the Poisson's ratio, and so on. Then we are computing the plastic strain sensor. VMove is another standard subroutine in Ansys. If you want to understand, go to help manual and search for say for example VMove. Okay, so if you go here, here is another nice place for guide to user programmable feature, is another very good place. Search for VMove. So it's moving one vector into another vector. Okay, so you don't want to basically define or write the entire Fortran program to do that. There are plenty of available vector function that can be used to do some of the vector operations. Okay, so if you are eventually trying to write some user programmable features either for material model or creating your own elements, it's highly recommended to go through this programmer's reference guide in detail. Probably it might take good amount of time to go through that. But however, I would highly recommend to go through that in detail so that you can understand what are the features those are available to you. Okay, and also plenty of examples available. User defined material example is available, and also there is an example for creating new elements, how we can create new elements and link it with Ansys and so on. Okay, then we are calculating the plastic slope, and also we are defining the hourglass stiffness effect, and we are calculating the elastic stiffness matrix. This is calculated for every integration point present in that element, and we are getting the initial stress, and we are getting the element data for every integration point. We are going into that and calculating the trial stress, then we calculate hydrostatic pressure, deviatoric stress, then compute the von Mises, compute the yield stress, then check for whether it's yielding or not, and compute the derivative of the yield function, initial guess for the equivalent plastic strain, finally you update the stress, update the plastic strain, and you can also update the state variables, and finally you could calculate the Jacobian matrix and so on. I'm not going into the details of the mathematics here because it is expected that you are familiar with the mathematics or the procedure in writing the constitutive model. So what I am trying to demonstrate here is that only the software implementation procedure, how do you understand the terminologies and so on. Okay, so having this done, this subroutine is available. What you have to do is that you have to copy this, whatever subroutine you are writing here. I am assuming that this is the subroutine you have written for now. So you have to place usermat.f inside this custom user 64 directory. Then you have to use the appropriate version of Intel Fortran compiler. So I'm going to use the Intel Fortran compiler from here. Yeah, it is important that when you are using the Intel Fortran compiler, you have to launch the compiler with admin privileges, because it is trying to modify some of the files in the C drive. So make sure this session has admin privileges. Okay, then switch your working directory to this folder. There is a file called anscustom.bat. Execute this anscustom.bat. What this is going to do, this is going to link this Usermat, compile and link with rest of the Ansys code. Okay, so there are special type of subroutines which is already provided by Ansys. We don't want to use this at this point of time for bilinear isotropic plasticity model implementation. I say no. So it says it's going to compile Fortran .f. What this is eventually going to do is that it is going to compile all the Fortran files present in this particular folder. Okay, so right now only one Fortran file is available, so it is trying to compile that. So as this compiles, it might take some time. I'm just waiting for that. So what this is going to do, it's going to compile and link, and it will update this ansys.exe. This ansys.exe is nothing but your custom executable. So once everything is successful, you will see the link is successful. It would say, do you want to copy the runtime DLLs? Yes, you want to. So the runtime DLLs are kept in some other location. When you say yes, all these runtime DLLs will get copied to this particular folder. Okay, now everything is done. So this is the Ansys exe, which can understand your custom defined material model. To use this material model, what you have to do, go to Ansys customization, go to Ansys product launcher, Ansys customization preference. Here is the custom Ansys executable path. At this location, you have to browse to this particular location and point to this ansys.exe. Once this is done, you are through. Okay, so once you are launching that, the other indication you have to look for is whether this custom ansys.exe is correctly accounted or not. When you look at the output file, you will see this particular keyword. Okay, note the Ansys version was linked by a licensee. If you see this note, it means that it is using the custom ansys.exe. And again, for this purpose, what I'm trying to do is that I'm trying to create a, a single element, single solid element. This is two solid 195 elements, single elements. So this block is modeled. There are two material models here. Okay, so if you look at the numbering for material number, this is with material number 1, this is with material number 2. Material number 1 is defined using the default bilinear isotropic Horning material model. Material number 2 is defined using user defined material model. Okay, so we are trying to pull this by certain amount, and it will develop the plastic strain. Then we are going to see the stress and strains from Ansys standard material model, and as well as from the user defined material model. So look at the results. I will close all these things. So this is going to list all this stuff. I will talk about this little later. You can look at the deformation is same. You can look at von Mises stress is same. You could also go and look at plastic strain, von Mises or any other plastic strain. They are exactly the same, 0.692 and so on, even the X component of plastic strain. This is a validation that whatever the user routine we have written is correctly accounted in the solver or the constitutive law. What we have coded is correctly accounted. Okay. Another thing is that I would like to show you is that this subroutine. So now this contains the, say for example, if you look at the 1D, the way we compute the plastic strain in 1D element is quite different. Okay, what we do is we will calculate the plastic slope. Elastic stiffness matrix is straight away from coming from the Young's modulus, and it is relatively simple compared to computing the plastic strain in case of a 3D elements. Okay, so this is the way how you can define multiple material models. So how it is going to identify is like this. So it will check for every element. If the number of integration point is greater than 4 for that particular element, it will call Usermat 3D. If the number of integration point is equal to 2 or equal to 3, then it's going to use plane stress based element. So like this. If it is equal to 3, then it will use 3D beam element, and so on. If you want to write multiple material models, put all those subroutines under each deck and use some kind of a reference to say which subroutine you want to call. Okay, say for example, if you want to write one single subroutine, it would look like this. This is a single subroutine. It will work only for, if you look at this thing, it has only one subroutine, not much. Okay, this is a Usermat. This will be called. There is no condition. Whatever element is there, it will try to call this subroutine. So straight away you don't want to define any conditions and so on. The mathematics involved here is same. The another important point I would like to highlight is the debugging option or the state variables. Okay, you can define many number of state variables as you want. Say for example, for this material model, I'm using TB state means the state variable. For material model 2, I'm defining 8 variables. We can use these 8 variables in whatever way you want. Say for example, here I'm assigning state variable 1 equivalent to the plastic strain. For whatever reason, I'm assigning plastic strain into 2 as state variable 2. Okay, it will be double. Say for example, if you want to debug and you want to know what is the stress state at particular point, you could assign stress of 2, I mean the SYY, as a state variable 2 also, or any intermediate variable. Say for example, constant 1 as a state variable 2, anything. then later we can go and print or plot these state variables. And also it is quite useful to write out some of the data into the output file. Again, we can go and look at the output file for debugging purpose. Okay, let us say originally I was having a subroutine, something like this, which is meant for all the files. Now what I'm going to do, I'm going to replace this subroutine with only for a single solid element. Okay, this will work only for a solid element. If your finite element model contains combination of shell or beam element, this will do the user defined material calculation only for solid elements. Okay, not for other element, or otherwise it will try to do for the other elements as well, but this constitutive law will not work good, so it will throw some error. Okay, so now this is my new stuff. Save this in thing and close Ansys. If you before you compile any user subroutine, you need to close Ansys version. Okay, yeah, come back here and execute ons custom.bat again. Now what it is going to do is it's going to compile the new subroutine. Okay, whatever changes that has been made. Continue, say no, it will compile. And other thing to notice is that when we are running this file, I'm directing all the outputs to some file. Let me check out. Yeah, all the outputs is directed to an external text file called user_biso.out. This is the user_biso.out for the last run. Let me clear this, it's blank. Do you want already runtime DLLs are copied? Copying it one time is fine, you don't want to copy it again and again. Now come and launch Ansys again. Now go and run this output file. So now what we are going to do is that we have defined 8 variables. Now in the time history post processor, we are going to get for element stress x from standard BISO material model and the user, and also same way for y direction and z direction, same way the plastic strain from BISO and user, and so on, all these things. And also we are going to print all the 8 state variables. Let's do this. Okay, now look at it. This is the state variable, what we are printing it. Let's look at one by one. This is from BISO, this is from user, SX. You can see that they are exactly matching for Y. This is how we can list any state variable for every node or every element. Okay, the second one compares the plastic strain in the x direction from BISO and user defined material model, same way for y and g direction, they all match exactly. And this is the state variable. State variable 1 is nothing but the plastic strain. So this is plastic strain, and state variable 2, what we have defined is that state variable 2 is nothing but 2 times the state variable 1. Where is that? Yeah, 2 times the state variable 1. That's what is coming. This is not used for any purpose. This is just for a debugging purpose. You could, as I mentioned, you could use this for any purpose. We haven't defined state variable 3, 4 or 5, 6, 7, 8, but as required, you can define as many number of state variables. Say for example, if you want to define a failure index as something like allowable plastic strain divided by the induced plastic strain, you know what is the allowable plastic strain, and you can define the ratio, and you can list it, and you can plot it also. Okay, this is state variable 1 versus equivalent plastic strain, they exactly match. And also it is possible to go and plot the state variables. Say for example, plot nodal solution state variable 1, you plot this. Okay, this material number 1 has no state variable, so it is all 0 values. But material number 2, state variable 1 is nothing but the plastic strain, so 0.2. If you plot state variable 2, it is going to give twice that of the plastic strain. If you plot 3, nothing is assigned 3, it will become, it's all 0 0, it's not showing anything. Okay, this is the typical procedure. And we have written out something to the output file. See, this WR enquire WR.output is the standard function. What it will do, it will understand what is the current output file. It will start printing the information to that current output file. So what I am doing, it will print for every element. Each element has, this is a hex element, so it has 8 integration points, so it is printing this for 8 times. Okay, I am from Usermat. Likewise, you can output any data into your output file and use that for debugging purpose. Okay, the another feature I would like to explain is how to use this custom features like custom material models or custom elements in workbench mechanical environment. We have seen that once the custom ansys.exe is compiled, it is possible to call that custom ansys.exe in mechanical APDL environment through customization and preference tab. If you want to use the same custom ansys.exe in Ansys workbench mechanical environment, set up the model as usual. You have to insert a command snippet under the body for which the custom material model need to be defined, and define like this. Define appropriate mechanical APDL commands to give required input for that custom material model. Then before hitting solve command, go to tools, solver process settings, my computer background or my computer. Go to this advanced tab. Once you go inside this advanced tab, it will have an option to specify the location for custom executable path. In this location, you point to this particular ansys.exe, whatever we have seen here. The same ansys.exe in the Win64 folder has to be pointed. Then say OK. Then say OK. Now if you go and solve, it will use the custom ansys.exe. This can be verified by looking at solution information. It will say this Ansys version was linked by Ansys. Now after this point, the solver is using the user defined material model in the exactly same way what mechanical APDL uses, okay, inside workbench mechanical also. I hope this explains the procedure or something kind of an introduction to how to use Ansys programmable features, taking bilinear isotropic hardening as example. So in this demonstration we have seen how to identify correct version of Intel Fortran and Visual Studio compiler, how to understand different input and output terms used by Ansys, how to get the inputs, how to pass the outputs back into the standard subroutine, and so on. Okay. Thank you.